What we're going to start to think about now is looking at other properties associated with vectors and pair of vectors in three-dimensional space. And what we're going to start to think about is how we calculate angles of vectors in relation to each other, so how we look at that. And in order to do that, we're going to start to look at something called the scalar product. Now this also has another nickname of the dot product, and you'll see why in just a second. But that's what we're going to look at. Now the scalar product of vectors allows us to use it as a tool to help calculate the angles between two vectors in 2D or 3D space. So it can't be used in 2 dimensions, but is generally extrapolated out at this level to work in 3D. Now imagine we've got two vectors here, a vector A and a vector B. What I'm going to tell you is the vector A is going to be given by the vector A1, A2 and A3, so 3 elements in A, and the vector B is going to be given by B1, B2 and B3. Now before we start building this up and looking at the angle between them, we have to understand what the scalar product actually means. Now scalar product is written like this, A dot B. Now this is again why it's called the dot product, because of this dot in between them. And this calculates a value. Now a key thing you need to look at is it's called the scalar product. Now remember, there's a difference between a scalar and a vector. A scalar is something with just a size, a vector has a size and a direction. Scalar product gets rid of that direction, so all you get at the end is a number. You get a numerical answer. So if you end up with a vector at the end, you've done something wrong. Now if I want to look at the dot product or the scalar product between the vectors A and B, and I tell you the vector A is of this form and the vector B is of this form, what we have to do is quite simply follow the formula A1 B1 plus A2 B2 plus A3 B3. So in order to do this, we simply multiply together the associated elements, so A1 and B1, A2 and B2, A3 and B3, and then add them all up at the end, so calculate the sum. Now take into account the signs. If there are negatives, these still go, so we could end up with A1 B1 minus something because one of the terms is negative. Be very careful because all that holds. It's not like magnitude where we get rid of this, it keeps that in play. If there's a negative value, it will have an effect in terms of that. A couple of examples just to show you exactly what I mean. I want to calculate scalar product of these two different things. So I want to calculate A dot B of this and P dot Q here. So A dot B of these two again is A1 B1 plus A2 B2 plus A3 B3. Now A1 is the first element, A2 is the second, A3 is the third. Same for B. So there's B1, B2, B3. So A1 B1 is given by 3 times 2 plus A2 B2. So A2 is negative 2 times B2, which is negative 3. And then plus A3 times B3, which is plus 5 times the negative 1. So 3 times 2 is 6. Negative 2 plus times negative 3 is 6 again. So it's then plus 6. And then 5 times negative 1 is negative 5. So it's plus negative, which becomes minus 5. 6 plus 6 is 12. Take away 5 gives me 7. Same sort of thing here. The only difference, instead of writing the vectors as column, I've written them in terms of I, J and K. Still the same sort of thing. So P dot Q, my dot product of them, is P1 Q1 plus P2 Q2 plus P3 Q3. And again, it's just the same sort of thing. So the I direction, there's your 1. The J direction, there's your 2. And the K direction, there's your 3. Now this one here, the I direction is my 1. My J direction, well, there is no J direction, which means that my second element is equal to 0 in this one. And my K, which is my third element, is equal to that. So P1 Q1 gives me the first term, so it's 2 times 3. Then P2 Q2 gives me the P2, which is just J, so that's 1, times the Q2, which is 0. P3 Q3 is given by this, so the negative 4 times the 2. And again, we plus there. So 2 times 3, that's 6. 1 times 0 is nothing, so we can ignore that. Negative 4 times 2 is negative 8. So that gives me an answer -2. Scalar product, dot product can be a positive or a negative solution. That doesn't matter. However, that can feed into the angular thing that we're going to look at and when we extrapolate it out. Now, I've said to you it allows us to do that, and it does. So if we then take our scenario and start to look at the angle theta between the two of them. Now, what I want to do in order to define this as well is I look at the vector here, AB. I want to know what the angle between the two vectors, vector A and the vector B is, and how I calculate that. Now, using the dot product or a scalar product, we are able to get this. So A dot B equals the magnitude of A, the magnitude of B, cos theta. Now we know what magnitude of A is, the size of the vector, magnitude of B, size of the vector, cos theta, where theta is the angle between them. So if I want to calculate the dot product of the angles, I can do that. I could also rearrange it to get cos theta, i.e. the size of the angle between the two vectors. And that's going to be given by A dot B over the magnitude of A, magnitude of B. So we can use either of these two when working in this sort of scenario. Now, there is a way we can prove this. However, in this video, I'm going to focus on the technique used within it. There will be another video you can go and look at if you want to look at the proof. Short video, but it'll show you the proof behind this formula and how we can work with it. Let's, though, look at how we can use these formula and how they can work. So let's imagine I give you the magnitude of A here, I give you the magnitude of B, and I give you the angle theta equals pi by 6, and I tell you that I want to know what A dot B is. Well, the first thing you need to do is pick the right formula. I know that A dot B is equal to the magnitude of A, magnitude of B, cos theta. In this formula, I want to know these three things. Well, I know magnitude A, I know magnitude of B, and I know what theta is. So this here is the version of the formula I want. All I need to do now is substitute in and perform my calculations. So I'm able to then say, fine, A dot B equals magnitude of A, which is √3, times magnitude of B, which is 4, times cos theta, so times cos of pi by 6. What I can then do is substitute in my values. Now this is where the exact values come into play. Cos of pi by 6, that's equal to √3 over 2. So I get √3 times 4 times √3 over 2. If I work all of that through, √3 times √3 is just 3, 4 times 3 is 12, divided by 2, it's 6. So my A dot B in this case is just given by 6. So that's us when we have the angle. But sometimes you're asked to calculate what the angle is. And that's this sort of scenario here. So I give you the magnitude of P, the magnitude of Q, and the dot product, so P dot Q, and I want to find theta, the angle there. So in this case, if I was to write down A dot B equals magnitude of A, magnitude of B, cos theta, I could tick off the A dot B here, the magnitude A and magnitude B, and this is what I wanted. So this is where rearranging it to cos theta equals A dot B over magnitude of A, magnitude of B comes in handy. This is how I want it to do. Now, if I gave you the vectors A and B, you'd have to calculate each of these bits on their own. So you'd have to calculate A dot B, magnitude of A and magnitude of B. However, I'm giving you that information, so you just have to substitute in. Again, one other thing to remember, I've given you the generic form. This is in terms of P and Q for this one. So actually, you need to think of it as P dot Q over magnitude of P, magnitude of Q. Remember, it could be written in terms of any set of variables, but it all comes down to this same generic formula. So P dot Q over magnitude P, magnitude of Q. I can then say, fine, so cos theta equals P dot Q, 5√2 over magnitude of P, which is 2, times magnitude of Q, which is 5. So 5√2 over 2 times 5, well the 5s can cancel. That's then equal to √2 over 2, which is the same as 1 over √2. So cos theta is equal to 1 over √2. I can then say theta is equal to cos minus 1 of 1 over √2. Cos minus 1 of 1 over √2, think back again to your exact values table. Theta equals pi over 4 or 45 degrees. We're not asked for specific degrees or radian measure. We can think of both in this case. Using either of these two formulas is fairly straightforward. We just have to remember the properties we know, the properties we're asked to calculate, and what our ultimate goal is, whether it's an angle or whether it's the dot product or even a magnitude of a vector.